Finding eigenvalues and eigenfunctions from the given Fredholm integral equation of second kind. Before doing that example, let me tell you what we did last time. We did in chapter number 3 all about the solving the integral equation having separable or degenerate kernel. This example. We did in the last lecture how we can solve the integral equation if it has the separable or degenerate kernel. Right now we're going to find out the eigenvalues and eigenfunctions of the given integral equation. First of all, what you have to do, you have to see that whether the kernel is separable or degenerate again. You can see that sine of x plus t can be split as sine x cos of t plus cos x sine of t. I have used the trigonometric identity here. After using the trigonometric identity, I have separated the integral into two parts because these two functions are adding up. So integral will be on the first part and then plus integral will be on the second part. After splitting the integral into two parts, we can see that this integration is depending on t. So you can take the x variable functions outside like this. After taking it out, you can see that you know that what we did in the last time method of degenerate or separable kernel. After taking the x variable out, you can take this complete integral as c1 and this complete integral as c2. We got this equation y of x lambda sine x c1 plus lambda cos x c2, equation number 1. Now your c1 is integral 0 to 2 pi cos t y of t dt. And your C2 is integration 0 to 2 pi sine of t y of t dt. I have written the C1 separately like this. Now you can see that you have y of t here. We had y of x already and y of x is all upon depending on x. So y of t will be depending on t. So lambda C1 sine of t plus lambda C2 cos of t. So I have written the value of y of t here. After using the value of y of t here, just simplify this expression, and after simplification this integral can be written with these two functions separately like this. After writing them separately, we have to integrate it, and after integration I will get this solution. And the limits of integration are from 0 to 2 pi, 0 to 2 pi. So first of all, in place of t, plug in the upper limit, then minus, plug in the lower limit. First of all, plug in the upper limit 2 pi in place of t, then sign minus, and plug in the lower limit 0 in both of these. And after simplifying, we'll get c1 equals to 0 plus lambda c2 pi. So I got this equation 2. Similarly, whatever c2 we took already, that is c2 is 0 to 2 pi sine of t y of t dt. Write it here and plug in the value of y of t again here. Your y of x is this one. So y of t will be, just replace the x with t. Plug in the value here. After plugging in the value here, separate the integrals into two functions and integrate it, apply the limits of integration, we'll get this equation 3. Thus, you can see that we have two equations, equation 2 and equation 3 in terms of C1 and C2. So we have a system of homogeneous linear equations. So for non-zero solution or non-trivial solution, we can take its determinant equals to 0. So first column is for C1, coefficients of C1, and the second column is for the coefficients of C2. So coefficient of C1 is 1 and C2 is minus lambda pi. 1 and minus lambda pi. Coefficient of C1 is lambda pi and coefficient of C2 is minus 1. Simplify it, just open the determinant. How we can open the determinant? Multiply 1 with minus 1 like this. 1 with minus 1. Then minus sign lambda pi with minus lambda pi and just simplify it. When I simplified it, I got the value of lambda equals to plus and minus 1 over pi. So we got two eigenvalues, lambda 1 positive 1 over pi and lambda 2 negative 1 over pi. So first of all, I am finding the eigenfunction corresponding to my first eigenvalue. So take it as lambda. You can mark it as lambda. Putting lambda is equals to lambda 1, 1 over pi in equation 2 and 3. We got the equation 2 and 3 previously. Just plug in the values of lambda there. When I will plug the values in both the equations, I will get these two equations. And from these two equations, you can see that C1 is equals to C2. You know, if I move this C2 on the right side, what I will get? C1 equals to C2. So whatever your function was, your solution was y of x equals to lambda sine x C1 plus lambda cos x C2. So now you know that your C1 is equals to C2. So just in place of C2, plug in the C1. So when I will plug in the C1, I can take the C1 common, and you know that you got the lambda as well. Lambda is 1 over pi, so take it common. Now you know this is some constant, so I am taking it as equals to 1. So I got the eigenfunction y of x equals to sine x plus cos x. Similarly, the same way we are going to do it by taking the other eigenvalue minus 1 over pi. Just plug in the lambda 2 is equals to minus 1 over pi in equation 2 and 3 again. When I will plug in this value of lambda, I will get these two equations. This one from equation 2 and this one from equation 3. When you move C2 on the right side, you will know that we have C2 equals to minus C1. Just rearrange it. So in place of your equation 1, just plug in C2 as C1. And put the value of lambda as well. You know, lambda right now is minus 1 over pi. After putting its value, take common and let minus c1 over pi equals to minus 1. Put the value here. After putting the value here, you can write it as minus 1 sine of x minus cos of x, or you can also write it as cos x minus sine of x. So this is the eigenfunction corresponding to this eigenvalue. Next time we will find the eigenvalues and eigenfunctions of the given integral equation if that kernel is the piecewise function. So we'll do it next time in the next video.